We will be discussing the current improvements that are being made in the field of tissue regeneration. Before we begin, we'd like to try and start by giving some background on this area. Currently, a number of amphibians are capable of using tissue regeneration to regrow damaged or missing body parts. This process is accomplished through the use of stem cells. In contrast, humans have a very limited number of organs that have this capacity to regenerate. Furthermore, the reconstructive capacity of these organs is very limited.
Part of the reason for this is because tissue regeneration in humans is facilitated by multipotent stem cells that are usually tissue-specific and only have the ability to heal small wounds. Burn injuries, ulcers, and other significant tissue damage are unable to be healed by the body alone. Therefore, there's a significant need for regenerative medicine that can assist in healing larger areas of tissue damage, such as those seen on the skin. Recently, studies have identified adipocytes, which are involved in fat storage and connective tissue, as a key player in the regeneration and homeostasis of human skin. Given these new findings, our research question became, how can we effectively use adipocytes to heal and regenerate severe and significant tissue damage in humans?
Wound healing consists of scar tissue with excess collagen and an absence of hair follicles with cutaneous fat. Researchers saw a large skin wound in mice regenerate hair follicles under WNT and fibroblast growth factor pathways and noticed new adipocytes within healed wounds. This led to question if hair follicles are necessary to establish adipocyte precursors. To answer this, they placed dermal cells from wounds in a culture that promotes adipocyte differentiation. They saw that dermal cells from wounds with regenerated hair follicles differentiated into lipid-laden adipocytes, but dermal cells from wounds without hair follicles did not, which led to the question of what is the origin of the new adipocytes. To determine the origin of the new adipocytes, they examined the lineage in mice and found that during wound healing, the new adipocytes in wounds expressed LAC-C, which indicated their origin from myofibroblasts. They then looked at bone morphogenic protein, BMP signaling, which induces adipogenic commitment of cells and grow hair follicles, which are critical for myofibroblasts to adipocyte reprogramming. BMP ligands showed upregulation of expression of active BMP signaling in dermal cells. They then studied a BMP antagonist, K14 noggin, in epithelial cells in mice to see if BMP signaling is influencing the regeneration of adipose. And you can see that after wounding, mice with K14 noggin failed to regenerate fat despite growing hair follicles. Taking all the results together suggests that wound myofibroblasts have the ability to convert to a completely different adipocyte lineage. Hair follicles grow independently of fat, and regeneration is necessary and proximal for cutaneous fat regeneration.
Cellular replacements for skin already exist, but there's a new focus on developing a skin barrier that is cellular. Cellular skin is advantageous because it can regenerate. The picture is of Epicel, which is one of the technologies used to develop a cellular skin. This is mainly used with burn victims. The patient's own skin is used along with mice cells to generate synthetic skin for the patient. However, Epicel does not change the patient mortality rate or the hospital stay time. 3D bioprinting is a new technology that can be used to layer cells on top of each other. Along with the different structures in the slides, 3D bioprinting could be used to create realistic skin in the future. This could be possible by 3D bioprinting adipose cells along with hair follicles so that the engineered skin can regenerate like actual human skin.